The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay. The other thing is, so the last lecture before the break ended a bit abruptly because I ran out of time. So just to summarize what the main point was, I mean, probably you figured this out, if you looked at the notes. It's not that important, but anyway, just wanted to remind you that, just to clarify what happened at the end, we got the diffusion equation from two bits of information. So the unknown in this partial differential equation is a function that we call u that corresponds to the concentration of some substance. And we used a vector field that represents the flow of whatever the substance is whose diffusion we're studying. And well, so we got two bits of information, one that came from physics that said that the flow goes from high concentration to smaller concentration, and that told us that the flow is proportional to negative the gradient of the concentration. And the second piece of information that we got was from the divergence theorem, and that's the one which I spent time trying to explain. And that one told us that the divergence of f is actually negative partial u over partial t. So when you combine these two relations together, that's how you get the diffusion equation. So I should say this is not the statement of the divergence theorem, but this is something that we derived from it with quite a few steps involved. And so what we got out of that is the diffusion equation, because we end up getting that partial u partial t is minus div f, which is therefore positive k times divergence of grad u, which is what we denoted by del square u, the Laplacian. So that's how we got the diffusion equation. Okay, anyway, I'll let you, have a look at the notes that were handed out in case you really want to see more. I just wanted to give the missing part of the last lecture. Okay. So let me just switch gears completely and switch to today's topic, which is actually line integrals and work in 3D. So that's going to look a lot like what we did in the plane, except of course there's a z coordinate. But you'll see it doesn't change things much when it comes to computing a line integral. It changes things quite a bit, however, when it comes to testing whether a field is a gradient field. So that's where we have to be more careful. So, okay, let's start right away with line integrals in space. So let's say that we have a vector field f with components, say, p, q, and r. And we should think of it maybe as representing a force. And let's say that we have a curve c in space. Then the work done by the field will be the line integral along c of f dot dr. Okay, so that's a familiar formula. And what we do with that formula is also familiar, except now, of course, we have a z coordinate. So we're going to think of vector dr as a space vector with components dx, dy, and dz. So when we do the dot product of f with dr, that will tell us that we have to integrate p dx plus q dy plus r dz. Okay, but it's still a line integral. So it's still going to turn into a simple integral, a single integral when you plug in the correct values. So the method will be exactly the same as in the plane, namely we'll find some way to parameterize our curve, express x, y, z in terms of a single variable, and then we'll integrate with respect to that variable. Okay, so the way that we evaluate is by parameterizing C and express x, y, z, dx, dy, dz in terms of a parameter. Okay, so let's do an example, just to convince you that you actually know how to do this, or at least you should know how to do this. So let's say that I give you the vector field with components yz, xz, and xy. And let's say that we have a curve given by x equals t cubed, y equals t squared, z equals t, for t going from 0 to 1. Okay. So the way we will set up the line integral for the work done will be, so before we actually set up the line integral, we need to know how we will express everything in terms of t and dt. So x, y, and z in terms of t are given here. We just need to do also dx, dy, and dz. Well, by differentiating, you get dx is 3t squared dt. That's the derivative of t cubed. Dy will be 2t dt. And dz will just be dt. Okay. And so we'll evaluate the line integral for work. Well, that will be the integral of yz dx plus xz dy plus xy dz, which will become, so yz is t cubed times dx is 3t squared dt plus xz is t to the 4 times dy is 2t dt plus xy is t to the 5 dt. Okay, so that just becomes the integral from, well, I guess t goes from 0 to 1 actually. And we are integrating 3 plus 2 plus 1, that's 6t to the 5 dt, which I'm sure you know integrates to t to the 6. So we'll just get 1. Okay? So it's the same method as usual. And if you're being given a geometric description of a curve, then of course you have to decide for yourself what the best parameter will be. It might be some time parameter t, like here. It might be one of the coordinates. Actually, here we could have used z as our parameter, right? Because in fact, this curve is x equals z cubed and y equals z squared. And we could also have used maybe some angle. Well, not here, but if we had been moving, say, on a circle or something like that. Okay, any questions so far? No? Okay. So, well, because, you know, we can do a bit more practice, let's do another one where we do the same vector field F, but our curve C will be going from the origin to the point 1, 0, 0 along the x-axis. So let's call that C1. Then to 1, 1, 0, let's call that C2 by moving parallel to the y-axis. And then up to 1, 1, 1, parallel to the z-axis. Let's call that C3. Okay. I'm sure that some of you at least are suspecting what I'm getting at here, but let's not spoil it for those who don't see it yet. Okay, so if we want to compute the line integral along this guy, then we have to actually break it into a sum of 3 terms. Okay? So, well, actually, maybe I should call that C prime, not C, because it's not the same C anymore. So I want to do the sum of the line integrals along C1, C2, and C3. And, well, if I look at C1, or at C2, actually. So C1 and C2 take place inside the xy plane. So, in fact, you know that z will be 0. And dz will also be 0 on both of these. And if you just look at the formula for line integral of yz dx plus xz dy plus xy dz, well, it looks like if you plug z equals 0 and dz equals 0, you'll just get 0. So these are actually very fast. Well, I'm not sure if well, okay, let me write it, but. Right, so this is going to be 0, this is going to be 0, this is going to be 0, and we'll get 0. Okay, now if we do C3, well, there we might have to actually do a calculation, but it won't be all that bad. So C3, well, x and y are both equal to 1. And of course, because they're constant, that means dx is 0, dy is 0. And on the other hand, z varies from 0 to 1. So if I look at the line integral on C3, well, so the first 2 terms, yz dx and xz dy, go away because dx and dy are 0. So I'm just left with xy dz. But because x and y are 1, that's just the integral of dz from 0 to 1. And that will just end up being 1. Okay, so if I add these numbers together, 0 plus 0 plus 1, I get 1 again. And of course, it's not a coincidence, because this vector field actually is a gradient field. I'm sure some of you have already figured out what it's the gradient of. Otherwise, we'll figure it out together. And so that's why, actually, we get the same answer for these 2 paths going both from the origin to 1, 1, 1. I mean, maybe I should point out, to make it clearer, if you plug t equals 0 in the path up there, you'll get 0, 0, 0. If you plug t equals 1, you'll get 1, 1, 1. So in fact, this vector field f that we have here happens to be conservative. And if you plot the 2 curves together, so well, I'm not really sure if I know how to plot this correctly, but I believe that, somehow, well, it's not exactly how it looks, something. Okay, whatever. So the first curve C goes from the origin to this point, and so does C prime, just in a slightly more roundabout way. So, they both go from the origin to 1, 1, 1. So it's not a surprise that you'll get the same answer for both line integrals. And how do we see that? Well, actually here, it's not very hard to find a function whose gradient is this vector field. Namely, well, the gradient of xyz looks like it should be exactly what we want. Right? If you take partial of this with respect to x, you'll get yz, then with respect to y, xz, and with respect to z, xy. And so, in fact, what was the easier way to compute these line integrals? Well, that was to use the fundamental theorem of calculus. We didn't actually, once we have this remark, we don't need to compute these line integrals anymore. We can just use the fundamental theorem. So, if we know this, the fundamental theorem, well, of calculus for line integrals, blah, 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 for line integrals. So that tells us that the line integral of a gradient field is equal to the value of the potential at the final point minus the value of the potential at the starting point. Okay, and that, of course, only applies if you have a potential. So in particular, only if you have a conservative field, a gradient field. Okay, so here in our particular example, well, so we have to look at, let's call little f of xyz that potential xyz. Then we take f of 1, 1, 1 minus f of 0, 0, 0, and that indeed is 1 minus 0, which is 1. So everything is consistent. Okay, so all this stuff so far works exactly as in the plane. Any questions? No? Okay, so let's try to see where things do get a little bit different. And the first such place is when we try to test whether a vector field is a gradient field. So remember, when we had a function of two variables, when we had a vector field in the plane, to know whether it was the gradient of a function of two variables, we just had to check one condition, n sub x equals m sub y. Now we'll actually have three different conditions to check. And that means, of course, more work. Okay. So what's our test for gradient fields? So we want to know whether a given vector field with components p, q, and r, whether it can be written as f sub x, f sub y, and f sub z for a same function f. And for that to possibly happen, well, we need certainly some relations between p, q, and r. And as before, this comes from the fact that the mixed second derivatives are the same no matter in which order you take them. So if that's the case, then I can compute f sub xy, which is the same as f sub yx, in two different ways. Right? F sub xy should be p sub y. F sub yx, well, since f sub y is q, that should be q sub x. Okay, so if you want, that's the part of the criterion that we already had when we had only two variables. But now, of course, we need to do the same thing when we look at x and z or y and z. So that gives us two more conditions. So p sub z is f sub xz, which is the same as f sub zx, so it should be the same as r sub x. And finally, Q sub z, which is f sub yz, equals f sub zy equals r sub y. Okay, so we have actually three conditions. So our criterion so a vector field F equals PQR. And here to be, completely truthful, I have to say defined in a simply connected region. Otherwise, we might have the same kind of strange things happening as before. So let's not worry too much about it, but just, for accuracy, we need our vector field to be defined in a simply connected region. And that means, for example, well, an example is just if it's defined everywhere. If you don't have any evil denominators, then you can just, go ahead, there's no problem. Is a gradient field exactly when, so we need three conditions. We need P sub z, well, let's do it in order. Let's P sub y equals Q sub x. And we have P sub z equals R sub x and Q sub z equals R sub y. So now how do you remember these three conditions? Well, it's pretty easy. You pick any two components, okay, say the x and the z component, and you take the partial of the x component with respect to z, the partial of the z component with respect to x, and you must make them equal. And same with every pair of variables. Yes. In fact, if you had a function of many more variables, the criterion would still look exactly like that. For every pair of components, the mixed partials must be the same. But we are not going to go beyond three variables. So you don't need to know that. This you need to know. Okay? So let me box it. Okay. So, well, that's pretty straightforward. Let's do an example just to see how it goes. Oh, by the way, sorry. We can also think of it in terms of differentials. Okay, so we can say, so before I do the example, let me just say in a different language, if we have a differential given to us of a form p dx plus q dy plus r dz is going to be an exact differential, which means it's equal to df for some function f exactly under the same conditions. Okay, that's the same thing, just in the language of differentials. Okay, so the example that I promised. Of course, I could do again the same one over there and check that it satisfies the condition, but then, wouldn't be much fun. So let's do a better one. So actually, let's do it in a way that looks like an exam problem. Let's say for which a and b is axy dx plus, oh, it's not going to fit here. Well, it will fit here. Axy dx plus x squared plus z cubed dy plus by z squared minus 4z cubed dz, an exact differential. Or if you don't like exact differentials, for which a and b is the corresponding vector field with I, j, and k instead, a gradient field. So let's just apply the criterion, and of course you can guess that what will follow will be figuring out how to find the potential when there is one. Oops. Okay. Well, so let's do it, one by one. So we want to compare P sub y with Q sub x. We want to compare P sub z with R sub x, and we want to compare Q sub z with R sub y. Okay, where we call P, Q, and R these guys. So let's see, what is P sub y? That seems to be AX. And what is Q sub x? 2x, okay? Q is this one. Actually, let me write them down because otherwise I'm going to get confused myself. So this guy here, that's P. This guy here, that's Q. And that guy here, that's R. So, okay, so this one tells us that A should be equal to 2 for the first property to hold. Okay, let's look at P sub z. That's just 0. R sub x, well, R doesn't have any x either, so that's 0. So this one isn't a problem. Q sub z, well, that seems to be 3z squared. R sub y seems to be bz squared. So b should be equal to 3. Okay, so we need to have a equals to and, this is an and, this is not or, b equals 3 for this to be exact. Okay, so for those values of a and b, we can look for a potential using the method that we are going to see right now. For any other values of a and b, we can't. If we have to compute a line integral, we have to do it by finding a parameter and setting up everything. Okay? Any questions at this point? Yes?
If QZ was 3BZ squared, how would you find it?
If if QZ was, oh, I see. Well, if I got the same answer, if I also got, oh, did you say bz squared or 3bz squared?
3BZ squared.
Well, 3bz squared, for example, then I would need b to be 0 because the only times that 3bz squared equals bz squared, as, not just at one point, but everywhere, I need them to be the same function of x, y, z. Well, that would be, if the coefficient of z squared is the same, that would give me b equals 3b, that would give me b equals 0. If you got bz squared on both sides, then it would mean, for any value of b, it works. And you wouldn't have to worry about what the value of b is. Okay, any other questions? No? Okay. So now how do we find the potential? Well, there's two methods as before. Okay? So one of them, I don't remember if it was the first one or the second one last time, but it really doesn't matter. One of them was just to say that the value of f at a point, let me call that x1, y1, z1, is equal to the line integral of my field along a well-chosen curve, plus, of course, a constant, which is going to be the integration constant. And the kind of curve that I will take to do this calculation will just be my favorite curve going from the origin to the point x1, y1, z1. And so typically it would be, the most common choice would be to go just first along the x-axis, then parallel to the y-axis, and then parallel to the z-axis, all the way to my point x1, y1, z1. So I would just calculate 3 easy line integrals, add them together, and that would give me the value of my function. Okay, so that method works exactly the same way as it did in 2 variables. Now I seem to recall that you guys mostly preferred the other method, so I'm going to tell you about the other method as well. But I just want to point out this one actually, see, it doesn't become more complicated. The other one, there's actually more steps. I mean, of course, here there's also actually a bit more steps because you have 3 parts to your path instead of 2, so you have 3 line integrals to compute instead of 2. But conceptually, it remains exactly the same idea. So I should say it works the same way as in 2D. Not much changes. Okay, so let's look at the other method using antiderivatives. So remember, we want to find a function little f whose partials are exactly the things we've been given. So we want to solve, well, let me plug in the values of a and b that will work. Okay, so we said a should be 2, so f sub x should be 2xy. F sub y should be x squared plus z cubed. And f sub z should be, so b was 3, so that was 3yz squared minus 4z cubed. So we're going to look at them one at a time and get partial information on the function, and then we'll compare with the others to get more information until we are completely done. Okay, so the first thing that we'll do, we know that f sub x is 2xy. That should tell us something about f. Well, let's just integrate that with respect to x. So let me write integral dx next to that. So that tells us that f should be, well, if we integrate that with respect to x, 2x integrates to x squared. So we should get x squared y, plus, of course, an integration constant. Now, what do we mean by an integration constant? Well, it means that actually for given values of y and z, we'll get a term that does not depend on x. It still depends on y and z. So in fact, what we get is a function of y and z. See, if you took the derivative of this with respect to x, you'll get 2xy, and this guy will go away because there's no x in it. Okay? So that's the first step. Now we need to get some information on g. How do we do that? Well, we look at the other partials. So f sub y, we want that to be x squared plus z cubed. But actually we have another way to find it, which is starting from this and differentiating. Actually, let me try to use color for this. So okay, so now if I take the partial of this with respect to y, I'm going to get a different formula for f sub y that will be x squared plus g sub y. Well, if I compare these two expressions, that tells me that g sub y should be z cubed. So now if I have this, well, I can integrate with respect to y, and that will tell me that g is actually yz cubed plus an integration constant. That constant, again, does not depend on y, but it can still depend on z, right? Because we still haven't said anything about partial with respect to z. So in fact, that constant I will write as a function h of z. So if I have this function of z, I take its partial, I will, with respect to y, I will still get z cubed, no matter what h was. Now, how do I find h? Well, obviously, I have to look at f sub z. Okay, so f sub z, well, we know from the given vector field that we want it to be 3yz squared minus 4z cubed. So in case you're wondering where that came from, that was R, okay? But that's also obtained by differentiating with respect to z what we had so far. Sorry, so what did we have so far? Well, we had f equals x squared y plus g, and we say g is actually yz cubed plus h of z. Okay, that's what we have so far. So if we take the derivative of that with respect to z, we'll get, well, 0 plus 3yz squared plus h prime of z, or dh dz, as you want. Okay, so now if we compare these two, we'll get the derivative of h. It will tell us that h prime is negative 4z cubed, and that means that h is negative z to the 4 plus a constant, and this time it's at last an actual constant, because it doesn't depend on z and there's nothing else for it to depend on. So now we plug this into what we had before, and that will give us our function f. So we get that f is x squared y plus yz cubed minus z to the 4 plus constant. If you just wanted to find one potential, you can just forget the constant. This guy was a potential. If you want all the potentials, they differ by these constants. Okay, so just to recap the method, what did we do? We started with, and of course you can do it in whichever order you prefer, but you have to still, follow the systematic method. So you start with f sub x, and you integrate that with respect to x. That gives you f up to a function of y and z only. Now you compare f sub y as given to you by the vector field with the formula that you get from this expression for f. And that, of course, this one will involve g sub y. So out of this, you will get the value of g sub y. When you have g sub y, that gives you g up to a function of z only. And so now you have f up to a function of z only, and what you will do is you will look at the derivative with respect to z, well, the one you want coming from the vector field, and the one you have coming from this formula for f. Match them. That will tell you h prime. You will get h, and then you will get f. Okay, any questions? No? Okay, who still prefers this method? Okay, that's still most of you. Who is thinking that maybe the other method wasn't so bad after all? Okay, that's still a minority. Well, you can choose whichever one you prefer. I would encourage you to, get some practice by trying both on at least a couple of examples, just to make sure that you know how to do them both, and then, stick to whichever one you prefer. Okay, any questions on that? No, I guess I already asked actually. Well, still no questions. Okay. So the next logical thing is going to be curl, and the theorem that is going to replace Green's theorem for work in this setting. That's going to be called Stokes' theorem. So let me start by telling you about curl in 3D. Okay, so here's the statement. So the curl actually is just going to measure how much your vector field fails to be conservative. And if you want to think about it in terms of motions, that also will measure the rotation part of a motion. So maybe I should say, well, let me first give the definition anyway. So let's say that my vector field has components P, Q, and R. Then we define the curl of F to be R sub y minus Q sub z times I plus P sub z minus R sub x times j plus Q sub x minus P sub y times k. And now, of course, nobody can remember this formula. So what's the structure of this formula? Well, you see, each of these guys is one of the things that have to be 0 for our field to be conservative. So by construction, if F is defined in a simply connected region, then we have that F is conservative is equivalent to if and only if curl F is 0. Okay? Now, an important difference between curl here and curl in the plane is that now the curl of a vector field is again a vector field. See, these expressions, they are functions of x, y, z, and together you form a vector out of them. So the curl of a vector field in space is actually a vector field, not a scalar function. Now, okay, so I've delayed the inevitable. I have to really tell you how to remember this evil formula. So the secret is that, in fact, you can think of this as del cross F. So maybe you've seen that in physics. So this is really where this del notation becomes extremely useful, because that's basically the only way to remember the formula for curl. So in fact, so remember we introduced the del operator. That was this symbolic vector operator in which the components are the partial derivative operators. So we've seen, well, if you apply this to a scalar function, then that will give you the gradient. And we've seen that if you do the dot product between del and the vector field, so maybe I should give it components, P, Q, and R. Well, when you do the dot product between these two vectors, you'll get partial P, partial X, plus partial Q, partial Y, plus partial R, partial Z, which is the divergence. And so now, what's new is that if I try to do del cross F, okay, so what is del cross F? So I have to set up the cross product between this strange thing that is not really a vector. I mean, I can't really think of partial X as a number. And my vector field PQR. So see, that's really a completely perverted use of the determinant notation. Okay? Initially, determinants were just supposed to be you had a 3x3 table of numbers, and you computed a number out of them. And now, I mean, okay, so these guys, well, they're functions, so that counts as numbers. But these are vectors, and these are, partial derivatives. It doesn't really make much sense, except as a notation. So if you try to enter this into a calculator or a computer, they'll just yell back at you saying, "Are you crazy?" But okay, so we just use that as a notation to remember what's in there. So let's try and see how that works. So the component of I in this cross product, remember that's this smaller determinant. So that smaller determinant is partial over partial y of r minus partial z of q. That's the coefficient of I. And that seems to be what I had over there. If not, then I made a mistake. Minus the next determinant times j. Remember, there's always a minus sign in front of the j component when you do a cross product. So the other one is partial x r minus partial z of p plus the component of z is going to be partial x q minus partial y p, and that's indeed going to be the curl of f. Okay, so in practice, if you have to compute the curl of a vector field, don't try to remember this formula. Just set up this cross product with whatever formulas you have for the components of the field, and then compute it. Okay? Don't bother to try to remember the general formula. Just remember this. Okay. So what's the geometric interpretation of curl, just to finish? So in a way, I will say just curl measures the rotation component in a velocity field. So an exercise that you can do, it's actually pretty easy to check. Say that we have a fluid that's just rotating about the z-axis uniformly. Okay, so your fluid is just, rotating like that about the z-axis. So if I take rotation about the z-axis, that's given by a velocity field with components negative. Well, let's say at angular velocity omega, that will be negative omega times y, then omega x and 0. And the curl of that you can compute, and you will find 2 omega times k. So concretely, this curl gives you the angular velocity of the rotation, well, with a factor of 2, but it doesn't matter, and the axis of rotation, at least the direction of the axis of rotation. It tells you it's rotating about a vertical axis. And in general, if you have a complicated motion, some of it might be, there's a translation, and then within that translation, there's maybe expansion and rotation and shearing and everything. And the curl will compute how much rotation is taking place. So it will tell you, say that you have, a very small solid, say, I don't know, a ping pong ball in your flow, and it's just like going with a flow. It tells you how it's going to start rotating. That's what curl measures. Okay, so on Thursday we'll see Stokes' theorem, which will be the last ingredient before the next exam, and then on Friday we'll review stuff.